No, it wasn't started. So we have some f of x, and I want to find the exact area from A to B. Now we have no clue how to do that. We don't. It's okay. Well, one of us knows what we're doing. But he doesn't have f of x, so he can't actually find the answer. Two of you do. That's true. You might have some false hope. So what I can do is, instead of coming up with an exact answer, I could draw some rectangles, right? Those rectangles, it could be a left-hand Riemann sum. It could be a left-hand point. You'll notice right here, we talk about how I want to find this area. We're going to partition this area and divide it into subintervals. Doesn't have to be equal subintervals, so these subintervals could be slightly different from each other. I could have some, I'm going to do another left hand here. Some intervals are going to be like this. Maybe I decide I want to have something that's not even quite a midpoint. And that's decided by this height. Yeah, we can get all sorts of crazy here. Maybe I create a thinner subinterval here, and I use a right Riemann sum. And what I'm trying to do is I'm trying to maybe balance my underestimates with my overestimates. So maybe I want to come up here, and I want to use like this point right here, and I really need to I've got a lot of overestimate over here, so maybe I need to estimate. And I could start making a whole bunch of rectangles, right? And all of these rectangles will eventually go together until finally I get all the way over to, I'm just going to cheat. My very last rectangle is very large. Actually, that's not a bad rectangle. Worked out pretty well. All right, so do you agree? If we take a look, yesterday we drew rectangles with the height, left endpoint or right endpoint or midpoint. Today I drew a bunch of rectangles. Some of them were left, some of them were right, some of them were midpoints, and the vast majority of them just wound up being wherever the heck I decided to put the point on the curve, right? All of these heights are independent of the left, the right, the midpoint. I just drew a bunch of rectangles, right? Now if we look at these rectangles, one of the things I want to do is I want to realize that like this would be my 1, my first, my second, my third, my fourth, my fifth point. These are all different intervals, right? So we could say that this interval right here, this is the change in the x, right? And how do we write change of x in mathematics? We call it delta, right? So we're going to call this delta x. But this isn't just any delta x. This is delta x of the first subinterval, right? And what would be the height of this first subinterval? Well, this would be our f of c. But this isn't just any c. This c is a constant, by the way. This is our first f of c. Agreed? So what would this second interval be? This would be delta x of 2. And this point right here, this would be our f of c of 2. And we could keep going, and we could label number 3 and number 4 and number 5, and we could keep going and going and going and going until we get way over here. And this right here, this is going to be our delta x, but I don't want to really count these. So I don't really know which subinterval this is. So I'm just going to call this my kth subinterval. It's some random subinterval that exists, right? Now if this is delta x of k, what does that make this? F of c of k. And you're going to feel a little dirty writing that. This is from a textbook. F of c of k. 100%. Every time. No, you cannot. Last period completely missed that connection. This period was like all over that. It's always the... Now, if I wanted to find the area of the first rectangle, what would be the area of the first rectangle? It would be delta x of 1 times f of c of 1, right? If I wanted to find the area of this second rectangle, that would be delta x of 2 times f of c of 2. So if I wanted to find the area of just any random rectangle, how would we state that? We would call that delta x of k times the f of c of k. Now, what if I don't want the area of just a single rectangle? What if I want the area of all of the rectangles? Not necessarily, because you're assuming that delta x of k and f of c of k are the same values.
Right. Delta x of n.
How do I find the sum of all possible rectangles? So how do I write that? Ah, there it is. The sigma thing. Oh God, I thought we got away from that. Little do you know, it's coming back with great vengeance and furious anger.
Oh, I know what this is. Has vortex.
So, I'm going to add together all of my x of k's times my f of c of k's, where my k is going to start at 1. And how many, and what, how far is that k going to go? To b, or in this case, how many exist? We don't know, so we're just going to say to n. What does n represent? N is the number of rectangles. By the way, I will tell you right now, when I started working with, now you're all, some of you are actually fairly well versed with sigma notation, so some of you probably are doing pretty well at it. If you're not feeling particularly well versed, I highly suggest making sure that you explain what these random variables like n are, or what k is. K is just whatever rectangle I am starting at, right? And it tells me what rectangle I'm at. What you've written here, this is no longer a left, right, or midpoint Riemann sum. What you have just written here is a legitimate 100%. This is not a left Riemann sum. This is not a right Riemann sum. This is not a midpoint Riemann sum. This is the true Riemann sum. Okay? It's right up there. This is the real Slim Shady of the Riemann sums. Now, here's the fun part. Oh yeah, wait, we haven't hit the fun part yet? We just put a sigma on the paper. That's not the fun part. Sigmas are pretty cool. Is that a perfect representation of the area between the curve and the x-axis from A to B? No, probably not. It could be. We'd have no way to verify that. I would have to make sure that my overestimates are perfectly balanced with my underestimates, which means I'm still going to have to find these weird areas of these gaps, which means I'm still going to have to do some weird work, and that's going to be tough, right? Is there a way that I can get the exact area under the curve? Of course, that answer is yes. So let me ask a different one. How can we get the exact area under the curve with AP Physics? Not necessarily. So the statement was, could we do a left Riemann sum and then a right Riemann sum? And then you said subtract them from each other until they get to 0 type deal. The first thing is you're going to have to keep doing left and right Riemann sums until you finally get one that when you combine them equals 0. So that the over and the under, but then they're going to be equal to each other. So again, you're going to have to know how much each of those Riemann sums is off by before you can determine if you have a correct answer. And if I can do that, didn't I already find the area under the curve? Ugh. What do you think? Infinite amount of rectangles. If I have a whole bunch of rectangles, then what's going to happen to each one of those rectangles? They're going to get smaller. The problem that we're running into here, if we made this rectangle here really tiny so we could pack a whole bunch of rectangles into this, do you agree that if I do that, then I wouldn't have an over and under estimate? In fact, we could make these super thin so we have not just a lot of rectangles, but an infinite number. Now, can we have an infinite number of rectangles? Yes, clearly. We can't have an infinite number of rectangles, but one of the things we can do is we can use the a lot of rectangles method. Now, if we get a lot of rectangles, what does that mean we're doing to our Riemann sum? If we're thinking of, here comes the board deciding that it's not going to actually write anything intelligent. Luckily, it's a sigma, so it's like, beep, beep, boop. Oh, come on, board. What? F of C, okay. Okay. Now here's my sigma notation. To do the pack a lot of rectangles, what would I have to do to that particular Riemann sum? Nope. Yep. As what goes to infinity? The end. Because what did I say? We said we're going to take the number of rectangles and we're going to get a lot of them. How many rectangles are we going to get? A lot. If we go to infinity, we're just going to keep packing in more and more. Now there's a second way you can think about this as well. There's two different schools of thought. You can either say that there's going to be a lot of rectangles, or we're going to say really thin rectangles. So again, we're looking at another limit. This time something's going to 0. But the problem is what would be going to 0 in the really thin rectangle argument? Delta xk is going to be our... Now, here's my question. I'm taking the limit as that delta xk goes to 0. Is the delta xk actually 0? No. The delta xk can't be 0 because if I have a 0 width, I don't have an area of a rectangle. So I have to have some width, but we can make that width really thin. No, not negative. So, what we have just done is we have defined what's called a definite integral. A definite integral is going to be this weird little squiggly line thing. That is called an integral. It is going to go from a to b of f of x dx. That dx, so I'll talk about that in just a second. And we can either look at it as having an infinite number of rectangles, or we can look at that as saying we let the width of the rectangles go to 0. And both of those would be acceptable ways to identify it. Now, what is all of this? If we take a look and we connect these, f of c of k is probably what part of this? f of c of k looks a lot like f of x. Agreed? All right. Where did the dx come from? As part of the limit, it actually has to deal with that limit causing this delta x of k to get very small. Think about when we did slope. What did we start with? We said that slope was delta y over delta x, right? But then when we introduced the derivative, we didn't say delta y over delta x, we said dy over dx. And all that meant was that the deltas had become incredibly small. Agreed? Well, what happened? The delta x of k has become incredibly small. That's where all the notation comes from. We have a definition here. It is, by definition, the definite integral is the area between the curve and the x-axis. Couple of things to note. F of x is going to be called the integrand. I am going to say that quite a bit. A and b are going to be known as my limits of integration. We need to know those. Dx is the variable of integration. Sometimes there will be a dx, sometimes there will be a dy. Sometimes we'll have dt. It just depends on the situation we're dealing with. All right? Other things to note. If f of x is always greater than 0 and a is less than b, okay, we're looking at a function. F of x is above the curve and a is smaller than b. Then the integral is really just that area. That's not bad, right? Now, what are some things you can tell me about area? There's one thing in particular that I want you to tell me about area. Because your geometry teacher has definitely said it before. You've probably heard about it in 7th and 9th, or 7th and 7th grade math for sure. Got to think about that. But that was a while ago. What do you know area cannot be? It cannot be meters cubed, because that's a volume. Areas cannot be negative. You cannot have negative areas. It is illegal. It is impossible. It is bad. But it's still a positive area, isn't it? Nah. Well, and that's the thing that we're going to talk about here. We do have to be careful. Yeah, exactly. Oh, God, no, never mind. I take it all back. Let's say I took the function f of x equals negative x on 0 to 4. So I would have the point 0, 0. I would have the point 4, negative 4. We would have this. So if I talk about the area between the curve and the x-axis, we're actually talking about this region right there. So far, so good? Okay. If I asked you to find the area of that triangle as it stands, what is that? B8. How'd you get that? Half of 4 times 4 is 8. That is the area. Agreed? Okay. Now, here's an interesting thing. That's an area. Integrals are actually, area would be an example of something that is a scalar. And this is where things get weird, because I'm going to make this point over and over and over again. I'm going to keep saying that the integral is the area between the curve and the x-axis, but some of these are not going to be positive. And what I'm mentioning here is this particular rule. In a Riemann sum, for every x of k and delta x of k, here's what I want to point out. F of x of k, can that be negative? Definitely. That's just a y value, isn't it? And can't y values actually be negative? So in this problem, even though the area is equal to 8, we would say the integral from 0 to 4 of negative x dx is going to equal not 8, but negative 8. Area is scalar. Integrals are vectors. We can have negative integrals. This is a fun thing when all my geometry people sit there and they start getting really upset because they've had pounded into their heads over and over and over. Area cannot be negative, area cannot be negative, area cannot be negative. I say an integral is the area between a curve and the x-axis, and then we get a negative answer. It doesn't have to deal with the area. It has to deal with the fact that because this is going in a negative direction. Now that's going to imply something else that's going to be in your homework, and I'm hoping some of you pick it up, and I'm not going to tell you what it is. All right. Also, another situation that could arise. I may have a situation come up where I have a curve. And some of the area is above, and some of the area is below. Let's call that B. From 0 to B. How on earth do I find the area between this and that? What? This is just B. 0 to B. What do you think? How would I find the answer to that question? We're not going to, it's actually not illegal to use trapezoids. In fact, trapezoids are a really good method of approximation. But we want to use something a little, we don't want to really think about the method of doing it right now as much as like how I would actually find this area. Let's say I knew what this area was. Let's say I knew what this area was. How would I find the area? Would I add those? Now here's the thing. Why did you say, I want to ask, why did you say add? Okay. Be careful of what you say here. I said I knew the area and knew the area. And if I say I knew the area here, technically this is a positive number. And you were thinking the same concept, but we have to be careful of that. And the reason why is that there will be questions on the AP test where I will give you an area above the curve. I'm going to give you an area below the curve. And you need to recognize that because I use the word area, I'm implying that the number is positive. But when I do the integral of the problem, it's a negative. I think you actually got asked, I think there was a question that was like this on the actual AP test too. It was kind of mean. So, as a practice, one of the things we can do is we can sketch a nonlinear function that meets the conditions on A and B. Labeling the area above the x-axis A1 and the area below the x-axis A2. So what do we have? We're going to have a function. It's going to have an area above the x-axis. It's nonlinear. It's going to be from A to B. So here's A. Here's B. There's B. And we're going to call this area A1. And we're going to call this area A2. So we would say the integral from A to B of f of x dx, the integral is going to be the positive area, or the area of the first section, minus the area of the second section. A1 minus A2. There's a really interesting question that if I don't ask it on a test, it will be on a review. And it's a really interesting question that's very similar to this. Good stuff. Cool. Questions on that? Because that was weird. Are we doing okay with my differentiation between area and integral? Okay. Should we see what it looks like in practice?
Yes.
All right. So in practice, this is what this looks like. In this problem, what is my f of x? This is my f of x, 1 minus x. And what are my endpoints that I'm going to go between? 0 to 3. I'm going to go from 0, 1, 2, 3. So what would be the endpoint for this left point at 0? It would be 1, right? And what would be the right endpoint? Negative 2. So we would have something that looks like this. And what we would be looking for is we'd be looking for the area total from here to here. We're going to call this A1. We're going to call this A2. My question to you, what does A1 equal? One half. How did we get that? 1/2, it has a width base of 1, it has a height of 1. Put it all together, you have an area of 1/2. What is the area of the second piece? Two. How did you get that? You took half of 2 times 2. So the area was 2. So if I look for the integral from 0 to 3 of 1 minus x dx, we know that that's going to be the area above the curve minus the area below the curve. Or in this case, 1/2 minus 2. What is 1/2 minus 2? Negative 3/2. Not bad. Just getting used to some stuff. This is all just getting used to little pieces here and there, making sure we know what we're doing. All right. That's okay. All right. My favorite part is the first line of this, actually. It is a fact that the integral from 0 to pi of the sine of x dx is equal to 2. You do not have to know that by memory, because you're going to learn how to solve that by hand later on. We're not there yet, so all I'm doing is giving this as a point of fact. This is a reference point. Nah. No, actually you don't. We're going to learn it before the end of the semester. With that information, and what you know about integrals and area, what you know about graphing curves, I would like you to determine the value of the following integral. So the first integral I'd like to ask you to find is the integral from pi to 2 pi of the sine of x dx. Using only your knowledge of what sine looks like, how to graph sine, and that the integral from 0 to pi of sine of x dx is equal to 2. You can answer this question. It is not 2. You are close. It is a fact. So let's talk about graphing sine. Where does sine start? 0. And at pi over 2, we would go up to 1, and at pi we would go back to 0, right? So when we talk about the graph from pi to 2 pi, what happens? It's the exact same graph, but it is now what's the difference between 0 to pi and 0 to pi to 2 pi? One's above the x, one's below, so this is. It's not 0. Why is the next one 0? Because one of them is above, is 2, and one of them is below, and that's negative 2, so we have a grand total of 0. Isn't this great? Doesn't even feel like we're doing math right now. We're just throwing numbers on a board. Just killing all the fun here. Yes. Yes. Destroy the fun. What about 0 to pi over 2? Waldo says it's 1. But why? Not Waldo. It's half of the first one. And since the whole thing is 2, half of that would be? This is great. Ooh. I like this one. What the heck? We should probably draw a picture.
Subtract 2 from both sides.
Then divide by 0. Now what's happening in this graph? We're moving it. Moving it where? What?
2 up.
It's 2 up. I'm not affecting the x. I'm affecting the outer portion of this, right? So f of x is 2 plus sine of x. So now we don't start at 0, but we start at 2. And if I go from 0 to pi, my final endpoint is also going to be at 2. Do you agree with that? Then somewhere in the middle, we are supposed to apparently hit 3, which apparently is really, really, really far up there. Now we know what this area is right here. What's that area?
No, you said just that area. You just said for brother.
So what's this? Isn't that 2 pi? Because that's a rectangle. Rectangle has a width of pi and a height of 2. So the total area of that piece is? We know that the region, this just got shifted up, right? So where this 2 is, that's this exact piece. So we're using composite figures here. We're saying we took that piece and we shifted it up. But then we still have this rectangle underneath. What is the area of that rectangle? It was a width pi long, and it's 2 high. So 2 times pi is 2 pi. So if this arch is 2, and this rectangle is 2 pi, what is the arch plus the rectangle? Done. What about 5?
It would be like this.
Before. Why? What happens in this graph? It's not that it goes through twice. Every single one of these numbers is twice as high. So the area is going to be double. The width didn't change. The height is now twice as high. What about 6?
Well, move it down.
Did we move it down to?
No, move it to the left. To the right. To the right.
This.
Oh!
This is shifting to the right by 2, right?
Correct.
That is 2 and pi plus 2. What do you think? Why is the answer still 2?
You shifted, and then you're shifting.
I took my limits. I shifted my limits to the right 2. But I also shifted my graph to the right 2. And if everything shifts to the right the same amount, it's still the same graph. Don't really care. What about 7? So think about what your function looks like. What? Yes, you do.
It'd be the same graph as number 2, but moved over.
Okay. Yes, we take a look. If we extend this back, doesn't this just come below? Well, so I have equal top and bottom. What about 8? We just answered all of these questions about sine, and now I'm going to throw a cosine at you. Haha, I'm back. There's now this random just dead spot in the middle of the video where there's just nothing. All right. Did we come up with an answer? Andy, you said 0. Why? Abel, you said 0. Why?
I said 0. I said 0. Armando
Gets
said
to 0 at 5 halves, and then gets to
So this and that are going to cancel out. And I don't care what the heck the answer to either of those is because they're going to cancel each other out and they're going to turn into a 0, and it's great. We are running out of time, so what I want to do is I want to give you the assignment, but then if I get a chance, I want to be able to finish one of these. The assignment is going to be to finish whichever ones I don't finish here, and to answer the what, like 15 questions that are after that? 21. You have all 21 of them to do. For real. All right. It is very fast. You will be fine. All right. Take a look at number 1. To be able to solve these, you are going to have to be able to draw pictures. What are my endpoints for this function? 0 and? All right. My f of x is 4x. So at 0, what would be my ordered pair? 0, 0. What is my point going to be at b? So I want to find the area between the curve and the x-axis. What shape did we make? Triangle. Area of a triangle is 1/2 the base times the height. What's your answer? 2b squared. Just her.
Don't worry, Keith, I'm going to give you the easiest test I can think of.
Okay, let's take a look at number 2, because number 2 is a little bit more rough, and it's going to take some getting used to with picture drawing. A is bigger than 0, so we're going to have some A value, and we're going to have square root of 3A. Oh, darn, you're going to have to figure it out. Ha, ha, ha. Folks, have a wonderful day.